this computer, and then I'm going to share screen, and I kind of know what causes it. It's me getting overly ambitious with the pen and the stylus, and I'm overloading my driver. And it's the only way to get out of that. And we are on like 18. Right. So the gate voltage is positive. It's going to put positive charge on this plate of the capacitor. Now, in order to accumulate negative charge on the source end, and here's the source because it's labeled as such, the body is tied to a P plus diffusion, generally tied to the source of a transistor is the best place for it. We'll talk about that a little bit more later. But if I put positive voltage from here to this part of the channel, the source part of the channel, I will accumulate negative charge there. So in order to turn this device on, I need to have some threshold, some VG, and since the source is grounded, VG equals VGS, because VGS is just VG minus VS. And in this case, VS is 0. So if VG is greater than VT, or VGS, let's do it the right way, is greater than VT, I will have enough voltage here to accumulate charge on this side of the channel. And that will be enough to turn it on. It will not be in cutoff. The transistor will be turned on. Now to decide if it's in saturation or triode. In order to put it, if I put it into triode, I need VGD. The other side of the drain needs to be greater than VT. And when that happens, I accumulate charge over here. And then I create this nice channel across there. Now, if we look at our curves, this is an important point, because it took me years. This was not intuitive. It took me years to get to the point that I understood this. If we look at our curves, this is what we typically call saturation. In saturation, I have a high VDS, which means I have a high VD in saturation. If I have a high VD, I have a low VGD. So this, when VGD is big, I'm actually in triode. And in triode, I have a channel of across both sides of the channel. The current, it kind of acts like a resistor at that point. As the voltage increases, the current increases. So it's looking resistive here because I have a resistive channel. What happens when I go into saturation, this makes everything so much easier. What happens when I go into saturation is this channel starts, the VGD gets smaller. So in saturation, VGD is less than VT because this D voltage has gotten much higher. And I start to pinch off the channel at this end, and I start to get something that looks more like this. So what is going on is that even if I increase the voltage, I'm not going to get any more current through there. It no longer looks like a resistor. The channel keeps getting shorter. It gets harder to get charged through this for this one, but it's got a higher energy. So the current starts to flatten out. And that is in saturation. Okay. Okay, let's make this smaller. Let me use my mouse, which is more reliable than my finger. Okay. So triode, it's acting, the channel's acting resistive. The resistance, GDS, is just 1 over RDS of the channel. It's changes with voltage. And it's going to equal Kn prime, which is the transconductance parameter of the transistor, times W over L times VOV. And VOV, if you don't remember from 280, it's an easy way to put a shortcut to a lot of these problems is to stick VOV in there. It's simply the difference between VGS and VT. So the resistance is proportional to how big VGS is. As VD increases, this is increasing VD, the channel keeps getting shallower at the drain end. Our channel goes up, the resistance goes up, the voltage is also going up, so the current stays fairly constant. Because the resistance is going up ideally by the same amount as the voltage is going up. Now we think about ideal sources. This is a curve, and I'm plotting the current versus voltage. Now, if I have a constant current, I've got something that looks like the blue line because it's constant on the I-axis. So this blue line is an I source, a current source. If I have a constant voltage, it's going to be a vertical line because now the voltage is staying constant and the current is changing. The current can be whatever I need to get out of the circuit, but that's the same thing. The green line looks like a resistor, V equals IR, and has a slope of R, so this is a resistor for the green line. When we compare these to the three channels of three regions of operation, when we're in saturation here, I've got this flat line. Saturation, the transistor looks almost like an ideal current source. A voltage-controlled current source is usually what we think about transistors in saturation. B, it's the old dependent sources from EE380 coming back to function. V-controlled I source. Now in triode, which is this region right here, it looks more like the slopey line. It's not a perfect straight line, but it looks more like a resistor than anything else. So as a first order approximation, I can look at this. The slope changes of that line as the voltage changes. So this is a voltage controlled resistor. This is one of the things we're going to use to build a linear model of this device. Never appreciated the first half of 280 until I had to build linear models of new devices, which is what I did and made myself a hero in the lab last semester. And yeah, never talk about the rest of it. I got to make fun of an ASU professor. Okay, my enjoyment in life. So we got three regions of operations, and the way I usually wrote this in EE280, that if for an NMOS transistor, if VGS is less than VT, then cutoff. This is just another version of that. I move VT over to the other side. If VGS minus VT is less than 0, then I'm in cutoff. Now there's a couple of ways we can figure out if it's in saturation. And the way I usually write it, because it's amazing when we get to analog circuits, is I write this. This is the way I do it. Here's my algorithm. VGS less than VT, then cutoff. If VDS is greater than or equal to, there is an equal to sign in there, because at the equal point, I call it saturation because the equations are easier. If VDS is greater than VGS minus VT, then sat. else triode. But I can rearrange that equation. I could flip it over to the other side and make that an equals. VDS greater than or equal to VGS minus VT. All I've done is flip it around. I could take VGS, I'm going to rearrange the equation a little bit, is VG minus VS minus VT, VD minus VS. So all I did is I turned the VDS into VD minus VS, the VGS into VG minus VS. I could add VS to both sides, making these go away. And then I could subtract VD from both sides, but VG minus VD is just VGD. And then move VT over, I get this equation. They're all really the same equation. I could take this equation, and I got to the second one just by doing this, adding VS to both sides, and I got to the third one with a little bit of rearranging. They're basically the same equation. This VGS minus VT shows up in so many equations. My shorthand, and this is put a big star next to this one and memorize it. I've got this thing called V over voltage, which is just the difference between VGS and VT. And I use those two terms interchangeably and don't even think about it. So get used to that. It's V over voltage is just VGS minus VT. I never liked that slide. Okay. So we got a bunch of transistors here, and we want to figure out what region of operation they're in. These are NMOS because they're outies on the source. So this is the source, this is the gate, and this is the drain. Okay. Determine if it's in cutoff. It is, and I want to get it in terms of VG. So I'm just going to take VG minus VS, and this is what you got to do in the homework, but this is like review stuff from 280. I could add VS to both sides, and the gate voltage would be VG less than VT plus VS. So I've got VT given up here. I've got the source voltage is 0 volts. So for this one, I would need VG less than 0.4 volts to put it in the cutoff. And I only have to know one terminal voltage this way. This is the advantage. I don't care about the drain because all I'm trying to do is determine cutoff. For this one, I need VG less than VT plus VS. VT is 0.4, VS is 1.2. So I need VG less than 1.6 volts to keep it in cutoff. And I'm sure you could figure out C at this point. And the solutions are in the slide solution if you want some more, want a little bit more practice. Now, if I want to solve this inequality and I want to put it in terms of VS, now I'm just going to solve this inequality for VS, and that would be I'd move VS over to this side, and then I'd have VG minus VT. So VS would have to be greater than VG minus VT. And I could go through here again. This is the gate. This is the source, and this is the drain, and I could figure out what the maximum value of VS would be for that circuit. Okay, so not so bad. Just playing with inequalities like we learned how to do in Algebra 1, or at least you did if you took my class. And yes, I used to teach Algebra 1. It was fun. I like high school students. They're so energetic and so honest. And they tell you exactly what they're thinking. Now, if I want to put this inequality in terms of VD, again, I have something that looks like VD minus VS greater than VG minus VS minus VT. I could add VS to both sides, and I'd end up with VD is greater than VG minus VT. So there is the inequality, and that inequality gives you the borderline value for VD, the minimum value of VD, to keep it in saturation. So the minimum value of VD to keep it in saturation is whatever VG minus VT is. And again, if I can label these transistors, gate, source, drain, and in this case, oh, they're all NMOS, then I can figure out the inequality. If I want to solve it for VG, I just take this inequality over here, move VT to the other side, and VG would be less than VD minus plus VT. So you guys can do all that. That's just arithmetic. For cutoff, we could go through the same process. In this case, if you wanted to solve this for VG, you would need VG greater than VT plus VS. And if I wanted to solve that inequality for VS, it would be VS less than VG minus VT. And you could figure out what all the what that would be. For saturation, to put it in saturation, the difference between PMOS and NMOS is the flip of that sign. For NMOS, it was VDS greater than VGS minus VT. For PMOS, it's VDS less than VGS minus VT. If I want to put the inequality in terms of VD, it's just VD less than VG minus VT. I've just added VS to both sides. If I wanted to solve this in terms of VG, I've got VG greater than VD plus VT. So that's pretty simple. If you just know that one basic equation, you can figure out all the rest. This is the way you saw it in 280, because this is the way I do it as an algorithm. For NMOS, VGS less than VT, you're in cutoff. Otherwise, VDS is greater than VGS minus VT, then you're in saturation, else triode. I could add or, this is an equivalent equation, VDS less than VGS minus VT for PMOS. So either one of those works for PMOS, or VGD greater than VTP. Otherwise, it's in triode. So for exam 1, that's one of the things you're going to have to be able to do pretty much on every problem, and especially on the first problem, is to be able to identify the region of operation of a transistor. All right. We want to determine the operating region. What have I got here? This is the gate, this is the source, this is the drain. It is NMOS because of the outgoing arrow. All this row is NMOS, all this row is PMOS because I have an ingoing arrow. First question I asked myself for NMOS is NMOS. Is VGS greater than VT? And my VGS in this case for A, whoa, what did I do? Okay, my VGS in this case is 0.2 minus 0 is 0.2. And my VT was given, it's 0.4. Is this greater than 0.4? The answer is no. So A is in cutoff. Now let's go to another one. I have a cheat sheet here so I can tell you which one's which. I can probably look at this point in my life, I can probably look at the transistors and tell you which one's which. 24. That's not right. Oh, I'm in the wrong. Sometimes it's easier to just look at the transistors and tell me what's going on. 24. Okay, so B, I'm going to do that one. If we look at B, is VGS greater than VT? So is 0.6 greater than 0.4? And the answer is yes. So it's not cut off. So I need to go on. The next question is VDS greater than VGS minus VT? VDS is 1, this is the drain, this is the source, this is the gate. So VDS is 1.3 minus 0, 1.3. VGS is 0.6 minus 0, 0.6. And VT's a fixed 0.4 volts. So that is true, it's in saturation. And get some practice with these. I can do them in my sleep, just about. Yeah, I can do them in my sleep. I do dream about things like this, unfortunately. The wild dreams of an electrical engineer. Get some practice, PMOS and NMOS, and you can check them against the answers in the answer key to get a good feel for what's going on. Something to do in that 6 hours a week that you need to study for this class. So yeah, we talked about the family of curves. If I'm in cutoff, you actually get a flat line down here. There's no current. If VGS is greater than VT, or it equals VT plus some overvoltage, you get a small amount of current. As VOV2 increases, increasing VOV, what you're getting is you're getting higher and higher along this family of curves. There are actually an infinite number of arrays of curves in between there. These are just examples at some particular values of VGS. And there are pieces of semiconductor test equipment that just do this. They take transistors and they measure these curves for you. And these are the guys usually building the transistors that want to measure these to verify that the process is working on that particular day. Some days it's not. Okay, now we want to calculate the drain current. First thing we have to do is it PMOS or NMOS? That's number one. Label the terminals. Body, source, gate, and drain. Body, source, gate, and drain. Then we want to calculate, we need to calculate VGS, VDS, and maybe VGD if it's PMOS, and put it into that little algorithm that I just showed you. And we can figure out the region of operation. Get region of operation. Is it in cutoff? Is it in saturation? Or is it in triode? Once we know that, we have current equations that these current equations actually work with both PMOS and NMOS. The thing is, in PMOS, this value is going to be negative. This value is going to be negative. This value is going to be the negative of a negative. This value is going to be negative, and this value is going to be negative. So you just have to be really careful with your signs, and you can use the same equations for both calculating PMOS and NMOS current. As long as I know the region of operation, this ID equals 0 is cutoff. It doesn't really equal 0, especially as transistors get shorter and shorter. There's leakage current. It may be picoamps, it may be nanoamps, but there's small amounts of currents flowing through and cutoff. And there's a whole nother, if you want to take device theory from Dr. Chen, who's teaching it now at the same time as me, we've got to fix that. You could learn more about that, but maybe some of you could take that next year from her. She's going to be a really good teacher. I'm glad we got another semiconductor person. If it's in saturation, I use this current equation. And if it's in triode, I use this current equation. Now, what happens at the boundary between saturation and triode when VDS equals VGS plus VT? These two equations actually equal each other, so you can pick which one to use. In that case, I choose the saturation equation because it's shorter. So I always just do this to make the students' head not hurt. That's the borderline. If it's equal to, I call it saturation. ID has absolutely no dependence on VDS. It's not in this equation. So in saturation, it doesn't matter how big VDS gets, the ID is going to remain constant. Here, I've got VDS terms, got two VDS terms in the equation. ID definitely changes with VDS. And here, it doesn't change with VDS because it's 0. Okay. Bias current practice. Again, you have to figure out what region of operation it's in. This one's in cutoff. So the current is 0. We already figured that one out. 0. If we went through, we've already done these calculations. Where were we at? 26. Which one's which? B's in saturation. Whatchamacallit? D's in triode. So the current's 0 in this case because it's in cutoff. That's good enough. For saturation, I look at this equation and I say, okay, for B, ID is going to equal Kn prime. I'm given a number 200 micro, so 200 times 10 to the minus 6. W over L is 10. VGS minus VT. My VGS is 0.6. VT is 0.4. And then I square it. So 0.2 squared. And this is number 26. I get the current. And the current comes out to be, for part B, 360 microamps. This is just plugging the numbers into the equation. D's and triode, so that's going to be a little bit different. So I'm going to do that one. My equation looks like this. So my Kn prime is still, oh no. 26. Sorry, my computer just froze again. That's when I get over enthusiastic with the pen. I will be back. I have to unfreeze my computer.